Welcome to the Friday Transportation Seminar at Portland State University. Today we're very pleased to have Jeff Hood with us. Jeff is the principal of Hood Transportation Consultant, and he will be talking about a rather technical topic today, but actually a rather important one for the travel assignment model. So we'll be talking about consistent estimates of route choice preference for dynamic transit assignment. With that brief introduction, I will leave the room to Jeff.
Hopefully everyone can hear me online. It's a great pleasure to be here. Thank you, Leming, for inviting me to talk here with you today. What I'm going to talk to you about is a project that I've been working on with the Metropolitan Transportation Commission, the MPO, in the San Francisco Bay Area, a collaborative project with them and the Puget Sound Regional Council in Seattle and the San Francisco County Transportation Authority with the Strategic Highway Research Program. They got a grant to implement a dynamic transit assignment model. And my role in this project is to develop a function which includes weights, parameters that represent the importance that transit riders place on different attributes when they're choosing a transit route. So the basic question we want to answer is, how do passengers choose a transit route? A transit passenger on their trip from home to work, for example, might have a variety of options to get there. And they might have to make trade-offs between certain attributes that are important to them. They might have a route that has frequent service, but when they get to their destination, they have to take a long walk in order to get to work. They may have a quick trip available, but it might be in a crowded vehicle. And so we want to be able to address the fact that somebody may not like to stand with a lot of other passengers. And in fact, they may not actually be able to board that vehicle at all if it's completely full. We want to be able to address the fact that a lot of people find traveling by rail more attractive, perhaps because of the comfort it offers compared to bus travel. And we want to be able to actually find out what the actual attributes of that travel on rail, what is it about that makes it more attractive, so that we can get away from just putting a constant in there which biases people towards traveling by rail. And then finally, we want to get at reliability. And my particular interest in this is in the reliability of time transfers, because I think that's a really important characteristic that would lead people to choose rail over bus. Is if at rail transfer stations, the transfers are often timed so that the trains are timed to get there at the same point, and they have a dwell time while they wait there, so that the probability of missing a connection or of having to wait a long time at that transfer is usually really low. So in San Francisco Bay Area, there's a system called the Bay Area Rapid Transit, which is BART. So basically, instead of a mode choice model where we try to predict the chance that somebody would choose BART, now given that somebody has chosen BART, we want to know how they're going to get to their destination on the transit system. And then once we have this, we can include that the route choice probabilities, the probabilities of choosing a route within a dynamic transit assignment model, where there's a feedback between the route choices that passengers make. The route choice model predicts the passenger load, and then the vehicle simulation model updates the travel costs for those passengers. And then there's a equilibration with the entire travel demand model, where the route choice model creates a measure of the desirability of taking transit to your destination, and then the travel demand model predicts the trips that people make, their mode choices. And when so that gives a table of transit trips, which then interacts with the route choice model, and then this entire model system is run in a large feedback loop. So the purpose of developing the route choice model within this system, there's two purposes. One is to predict the number of passengers taking different transit routes, and also to create a measure of the desirability of taking transit between an origin and destination for the demand models. So my presentation is going to get pretty technical soon. So what I'd like to do is I have divided into sections. I'd like to save the questions, online questions, for the end of the presentation. But if anyone has any questions about the purpose of this project that I've talked about so far, I welcome you to ask them as I go along. Is what I'm describing here clear? Or does anyone have any questions about it? Okay, great. I'll move on then. So here's the outline of my presentation. I just gave you the introduction. Next, I'm going to talk about the limitations of path-based models, which is a class of methods that have been used predominantly in the field of route choice modeling for, I don't know, a decade or so. There's a lot of limitations to them, and I kind of think this is a dead end, actually, and so I'm going to explain why I think that using a path-based model is a dead end. And then I'm going to talk about the recursive logit model, which was a breakthrough that was developed by, I don't know how to say their names because they're all European, but Foskerau, Freyinger, and Karlstrom a couple years ago. And it's I'll go into that when I get there. And then I'm going to talk about a new correction for the route overlapping problem. There's a big issue in route choice modeling because the routes actually overlap with each other, and the probabilities that people choose a certain route, the random factors that influence that are actually correlated, and we have to use methods to correct for that. And I'm going to present the results of a new correction for that. And then finally, I'm going to talk about reliability and stochastic vehicle arrivals. So first, the limitations of path-based models. A path-based model is basically a model that looks at entire paths from an origin to a destination rather than individual blocks or individual links, individual vehicle movements in the transit network. So it will look at one path and another path and then calculate the probability that I'll choose that entire path versus the first path. And the problem with these models is that in a regional scale network, there's just so many paths that you can't enumerate all the possible paths in the network. I mean, there's essentially an infinite number of paths. And so these models require the analyst to generate a choice set, a subset of paths in the network that the modeling passenger will choose between. Here's an example of the result of a choice set generation method that I developed for San Francisco County Transportation Authority. They had collected some GPS data with an iPhone and Android app called CycleTracks, collected GPS data from cyclists to try to understand how they choose their bicycle routes. And in black here, with the circles, you can see, actually I guess it started here, you can see the cyclist's route to their destination. And then in the colored lines here are all I think there's like 96 different routes that the person could have chosen instead in order to get to their destination. And then by comparing the attributes of the chosen route to all these other different routes, then we can try to understand what's nice about this route that isn't nice about all the other routes, and why cyclists would choose that route. The problem with this method is that it's a stochastic sampling method that has an unknown sampling distribution. So we can't calculate the likelihood that any one of these particular routes would end up in this choice set. And there's a lot of methods like this, and there's a branch and bound method. There's a link elimination method. It's just like over the last 10 years, all these different researchers try to come up with the method that hopefully is going to get a good result here. And the problem with almost all these methods is that they don't result in a consistent estimator. And so for most of these choice set generation schemes, the estimators are inconsistent. And a consistent estimator is really the base minimum requirement of a statistical estimator for it to perform reasonably. So when I say consistent, I mean, when I'm trying to get a consistent route choice estimation, I mean a very specific thing. With the consistent estimator, the distribution of the estimate approaches a limit in probability as you collect more and more data to the true value. So this is, and on the x-axis here, I have the difference between the estimated parameter and the true parameter. So I'm supposing that I collect more and more data. So I get one person's route, 10 persons route, 100 persons route, 1,000 people's route, and then infinitely many people. I sample everyone in the entire population every trip. And as I collect more and more routes, the sampling distribution for my estimator is going to approach the true value in the population. If you have an inconsistent estimator, then, I mean, it's really basically, you don't know if it's any good or not. There's no way to know. Not only might it not approach the true value, but it might not even converge at all. So it's this value, an estimate of this isn't really very useful for any practical purposes. It's kind of like this cartoon that I found at a meteorological office, weather forecaster, and the one forecaster says to the other one, "With our new super fast computers, we can get the forecast wrong twice as fast as before." So I think, unfortunately, I think that happens a lot in practice, that there's a constraint about what can be done, and a lot of times modeling methods are kind of crammed in to fit into that constraint. And it's just, if we end up in that situation where, because of administrative needs or because of computational issues, we're actually introducing a lot of bias, then I think it really does a disservice to the public, and that's my number one priority, is to avoid that. There are consistent methods of path-based route choice modeling. This shows an example that was developed by SFCTA later to try to correct for this limitation. And this, on the left-hand side here, there's the example route choice sets between a base scenario where there's really no attractive options and a lot of different paths are generated because of that, and a build scenario where a new bike lane was put on Valencia Street in San Francisco. They were doing backcasting, basically, to look what happened, to see if it predicts the correct value after this improvement, which was already done. And with the stochastic sampling, the total choice set size is smaller because almost all the paths use the bike lane now. And so if one of the tenets of econometrics is that having more stuff, more options is better. So if there are fewer options here, then the attractiveness of cycling is going to go down. And so it's not a great position to be in when you're telling the planning department how their bike lane is going to perform if they've made an improvement, and then you're actually predicting fewer bike trips. That's not going to go over very well. So they developed a method which generates several routes to the destination, but every time it calculates the total size of the choice set, and it penalizes routes that overlap with the ones that are already in the choice set. And by doing that, they can generate a choice set with a consistent size in between observations or alternatives, and then at least empirically, it appears to be consistent. There are other consistent methods. There's like one that's based on a biased random walk, and another one which is like kind of stitches paths together and follows a Bayesian Metropolis Hastings resampling thing, which I think they're important because they established a consistent method, but the problem is that they all take a really long time to run, because this method that I have up here is the choice sets have to be generated for every origin-destination pair. The method that I showed you before, you can generate choice sets from one origin to all destinations, but this one you have to repeat it for every single destination and every single origin. And so the runtime is quadratic in the number of zones in the planning system. So with just 1,000 zones, that's only in the county of San Francisco, let alone the entire Bay Area. It takes a week to run on a reasonably good computer, which is just unacceptable. So a few years ago, my perception of path-based route choice modeling research looked like this. There's all these ideas, people are generating all these ideas, and maybe one of them will pan out. Good luck. This is a direction sign I'd found on the internet. I don't know if it's actually real or if it's a joke or what, but now my perception of this area of research looks like this. I really just think it's a dead end and that we need to turn back and find something new. Does anybody have any questions about the path-based route choice modeling paradigm at this point? Okay, I will go on then. So there's a breakthrough a few years ago called the recursive logit model, which it basically connects a path-based choice model over all alternatives in the entire network with a link-based paradigm where we're just looking at one single choice to board this transit vehicle or to go down this block instead of that block, turn left or turn right, instead of looking at the entire path. And it's based on a dynamic programming solution to a Markov decision process. A Markov decision process it's like a Markov chain where there's probabilities from going from one state to another, but there's also a decision maker that is influencing those probabilities. So there's factors which are leading to randomness, which the decision maker has to navigate, but then also the decision maker is exerting some control to choose an alternative. So the state here represents the place where I am in the network. So if the K here is the current link in the network, and the decision maker is making a choice between all of the possible movements from K, which are in the set of links A of K, the set of links that are accessible from that link, the set of successors. And so the decision maker is trying to get from the current link K to the destination D. And it makes a choice among these links based on the expected utility, capital V, from the end of the link to the destination. And it makes that choice by maximizing that expected utility over all these alternatives to get to the destination. And then it adds another instantaneous utility from moving from, this should be the other way around, moving from K to A. So the decision maker looks at, the utility can be based on the time to get down this block. If I turn left here, then to get to the end of that block, it's going to take me 20 seconds. If I turn right here to get to the end of that block, it's going to take me 30 seconds. And then that component of time is added to the expected time to the destination after I get there. So I get 20 seconds to go down this block, and then over all the possible paths that I could get to my destination, what's the expected time for me to get there, and then I add those two together. So the traveler is maximizing the sum of the instantaneous utility for this one choice and the expected downstream utility to the destination after I make that choice. So that's expressed in this recursive value equation. The value at link K is the expected value of the maximum of the instantaneous utility plus the expected utility to the destination and a random error. Now, if the random errors are identically and independently distributed extreme value type 1 or Gumbel random variables, then you end up with a logit transition probability. So the probability that I choose link A from link K is a logit of the deterministic instantaneous utility plus the expected utility to the destination. And the solution of this value equation then is the log sum, which the log sum is in a logit model or with an extreme value random variable is the expected maximum utility over all of my options. So the real contribution here that Voskurow, Karlstrom, and Freinger made was to figure out that these solutions can actually be solved really efficiently if we do a little algebraic trick, then we can actually express them as a linear system that is really easily and efficiently solved. So if I create a matrix of the exponentiated instantaneous utilities, so I just, in every location in that matrix, so on the columns I would have the link that I'm coming from, and on the row I would have the link I'm coming from, and in the column I would have the link that I'm going to. Then I just fill each of the entries in that matrix with the exponentiated instantaneous utility from going from one link to the other. And then I have an indicator vector for the destination, so it's just got zeros everywhere except for the destination link. And Z then is the variable that I'm solving for. It's the vector of expected maximum utilities to the destination for all origins in the entire network. Then I forgot to. Bellman was the guy who developed this Markov decision process, dynamic programming, but I changed that on the other slide. So that's where the Bellman comes from. I call that the recursive value equation in the last slide. So Bellman's recursive value equation can be expressed as a linear system of equations. And so because this system is sparse, each link only connects to a certain, maybe just a handful of other links, then the system can actually be solved really efficiently. The solution time is linear in the number of links, which is actually better than a path search. Dijkstra's algorithm is, it's linear, log linear. I don't know what you call that, but it's linear times the log of the number of links. So this is actually even faster than that. And then the result is also equivalent to a path-based model with an unrestricted choice set over all alternatives in the network, with the additional requirement that the utilities are link additive or link pair additive. So in the transit case, that would represent a transfer. So the utility can depend on the transfer from one vehicle to the other, but it can't depend on a sequence of 3 transfers or more transfers. So that's the kind of the limitation that we have to accept in order to use this model. Does anybody have any questions about the recursive logit model at this time? Okay. So The problem with the recursive logit model in its initial development was that there wasn't a clear way to correct for route overlap. In the path-based paradigm, if we generate several paths, then we can measure how much they overlap. But if I just am looking at each link individually, it's not clear how I can measure the overlap and correct for that. So that's what I'm going to talk about now is the new method that I developed for this project to do that. So I guess first I'll just describe this issue with talking more about the path-based paradigm. One of the assumptions that I presented earlier in the recursive logit model was that the random errors are independent of each other. And that's not really accurate in reality. In reality, the random errors are correlated wherever the routes come together and overlap with each other. So what I have here are two example networks. One where the errors would be uncorrelated with each other because the degree to which they overlap is very small. There's 3 routes here. You can get to the destination via link A, or you can get there from B going to C, or you can get there from B going to D. So the routes BC and BD overlap with each other on link B, but because link B is kind of inconsequential, it just represents me walking out my front door, for example, and do I turn left or right there, then the errors in that network are going to be uncorrelated with each other. But if the degree to which they overlap is very high, then the errors are going to be correlated with each other, and we need to account for that fact. In the path-based modeling framework, this was done with a path size variable, which basically is the inverse of the number of paths that use a link. And so the size correction in the uncorrelated case, there would be no correction. The size of each path would be 1. And so the probability that I would choose each of these routes would be 1/3. The demand would be equally spread among links A, C, and D. In the correlated case, if C and D links are inconsequential and don't really matter, and it's really a choice between A and B, then the size of the paths B, C, and BD will be 1/2 because there's basically 2 paths which use link B. So the size of the paths is reduced by the inverse of that. So each of those alternatives would really seem like half a choice. And then when you add the demand for those 2 together, you would get a full alternative. So the demand in this case goes 50% of the demand would go to link A, and 25% of the demand would go to each of the B, C, and BD alternatives. But then when you add those back together, you get half of the people going on A and half of the people going on B. This, of course, assumes that the utilities of these routes are equal with each other. So for the recursive logit model, there wasn't really any clear way to do something similar, and the researchers who developed that model, they recommended just using the link flow as a proxy for the overlap, because if the link flow is very high, then you're probably at a place where the routes come together and overlap with each other. I wasn't super satisfied with this option off the bat, and so I tested it in some illustrative examples, and I found that it did perform poorly, and I can think of some reasons why it performs poorly. First of all, it's not sensitive to the extent of the overlapping link. In the previous slide, I showed you how if the overlapping link has a large extent, then there should be a large correction. If it's small and doesn't overlap very much, then there shouldn't be any correction at all. It also conflates the route overlap with the route utility. Sure, if paths are coming together, my flow would increase because the paths are overlapping there. But my flow also might just be really high because it's a really good alternative, and I don't want to penalize that alternative for no reason. It also requires a scaling parameter. You have to estimate a coefficient to apply to it, and that coefficient is not independent of the network you're using. It's not topologically invariant. If you use, estimate a model in one network and then estimate the model in another network, you're going to get a different coefficient. And then that coefficient, even in the same network, is not going to apply perfectly to all of the different choices. It's only going to be an average that works overall. So what I did is I developed new link size variables which extend the recursive approach to the counting of paths. What I have here is an equation which represents the number of path segments that are available to me downstream of my current link. So ND is the number of downstream path segments. And I can calculate that very simply if I know the number of path segments for all of my successors. So I just look at all of my successors, and then I add up how many paths are available from those alternatives. And then by adding all up the paths for all my successors, then I get a recursive equation for the number of paths which are available from the link which I'm on. And then you can do the same thing for the number of upstream path segments. And then the number of paths which contain my link is equal to the product of the number of downstream path segments times the number of upstream path segments. It's just combinatorics. The issue with this, one of the issues with this approach is that the equations have no solution in cyclic networks. If there's no cycles in your network, if you can't go around in a loop, then these equations will have a solution that can be found efficiently with the same methods that are used to solve the linear recursive logit model. I mean, this is just a big matrix equation. If there's if there's cycles in the network, then they're not going to have a solution. I mean, you can just, if you imagine expanding the sum in the equation, then you're going to have a coefficient of 1 for the number of paths on the current link on both sides of the equation, and there's going to be no way to solve it. Well, luckily, the path counts should actually be scaled by the probability of choosing those paths anyway. So if we scale the path counts for the downstream links by their probabilities, then these equations are going to have a solution in cyclic networks. And also, I'm going to show in a bit that this method more closely reproduces theoretically correct results from a nested logit model anyway. So in this equation, I'm calculating the probability scaled number of paths to my destination. And what I do is I look at all of my successors, and then I scale the number of paths available from that successor by the ratio of its probability to the maximum probability of the alternatives that are available to me. And so basically what that does is whatever link has the highest probability, its scaling factor is 1. So all of the paths that are going through that link count in their entirety. But then if for a link that has a lower probability, that the amount which I account and accrue those paths to my current link is reduced by the ratio of those probabilities. Here's an example illustrating this recursive formula. So here I have my current link. Just ignore this math over here for a second. And I'm trying to get to my destination. And I have two successor links that I can use to get there. And I don't really know what this part of the network over here looks like. It's something unknown. But I know that I have 3 paths available to get to my destination this way, and I have 2 paths available to get to my destination this way. Now, so the total number of paths from my link is then 5 if I just add those 2 together. But one of these alternatives has a much higher probability, so the paths are all better this way. So those should count more than the paths which aren't good. So no, I'll just go into the formula. So the scaled path count for my current link, for the link with the highest probability, it counts fully. So I count all 2 paths. I get 2/3 probability divided by 2/3 probability, which is the maximum multiplied by 2, and I get 2 paths for this direction. But then I scale the paths in the other direction down by the ratio of the probabilities of the links, so that those 3 paths get divided by 2, and they only count as 1.5 paths. And then, in the end, I add those together, and my kind of equivalent number of paths to get to the destination from this location is 3.5. So if I had 3.5 completely independent paths that didn't overlap with each other, then basically the desirability in that situation of getting to my destination would be equivalent to having these paths that overlap with the varying utilities. And finally, we use these probability scaled path counts to develop link size variables which follow the established form from path-based methods. So the link size variable is the extent of the link, m of k, divided by the expected measure of all paths going through that link. Measure here represents something like the length of the link or the time of the link. That, when I showed you the network before that had a very long link and a very short link, that's what the measure is supposed to represent. So it's basically like the percent of my path which this link represents. So I take that percent of my path which this link represents, and then I multiply it by the logarithm of the product of the upstream and downstream path counts. So I have some examples illustrating this method, to just little toy examples here, to compare this method with some other methods that are available. The first represents collapsing downstream alternatives. So basically, link A has a travel time of 1 and a measure of 1. The measure right here is actually just equal to the travel time. And then the measure and travel time on link B is changing. So it goes from, variable, and it goes from 0 to 1 here, I'm assuming. So basically, B, it's like an accordion. Like, this network is expandable. So B will grow or shrink, and then the amount that the paths BC and BD will overlap changes. So here's the flow on the upstream link B as a function of the travel time on link B. So 1 here represents perfectly overlapping, so that those 2 paths are identical with the link, and 0 represents no overlapping. So here's different methods which we could use to correct for the route overlap. One is the proposed method that I've described here. One was the initial unscaled path count. So this is just using the actual number of paths going through the links. And then LS flow here was the link flow proxy that was recommended by Foskerow et al. And then finally, there's a nested logit model. In this little toy network, we can actually perfectly calculate the theoretical result from a nested logit model, which isn't possible in larger networks. But here you can see that the proposed method and the unscaled path counts, using calculating the size variable this way, both the elasticity, the changes here, the change in flow on link B is perfectly matched with the nested logit model, whereas the flow, which was the flow proxy, which was calibrated to match the result when the travel time is equal to 1, it's completely insensitive to the extent of the links. It doesn't care at all, so it doesn't change. Next, I have another example looking at the same network, but where the utilities downstream change. So, again, link A has a travel time of 1, and now if the alternative BC also has a travel time of 1. It just stays the same. And the measure of link B stays the same. So the network isn't accordioning anymore. The extent of link B stays the same. But now what changes is the travel time on link D. So basically, maybe there's some congestion on link D here, or there's a transfer here and people don't want to wait. For some reason, just link D starts becoming really unattractive. In this case, in the limit, we want a solution that is identical to the solution that you would get if link D didn't exist at all. Like if link D becomes really bad, then you should end up with the same solution if just link D weren't there at all. And so that's what I wanted to test with this example. And this shows the predictions that you would get with these different methods for this example. So on the y-axis here, I have the flow on the upstream link, and then on the x-axis, I have the travel time on that link that starts to look really bad as I go towards a travel time of 1, which is really high compared to the other alternatives. Then link D starts to matter less and less. The proposed link size method now is the only one that gets that limit correctly, where as link D starts to be really bad, that the probability of going on link A or link B approaches 1/2. All of the other methods, basically they overcorrect for the overlapping problem and put too much of the demand on the non-overlapping link. Does anybody have any questions about the path overlapping problem or the correction? Okay. I was uncertain whether I would actually have time to discuss this or not then, but I will go ahead and launch into this issue. The project sponsors for this were really interested in addressing reliability. That's one of the goals of the Strategic Highway Research Program, is to develop a way to measure reliability of the transportation network and how people respond to that. And reliability, most of that research, it's a Strategic Highway Research Program, most of that research is focused on highway travel and the experience of the private motorist. And I had to go back to 1993 with Mark Hickman's dissertation to really find anything that helped me figure out how to measure reliability in the transit network, because the problem is much more complex than reliability in the highway network. So the reasons that traveler responses to reliability are more complex for transit is that poor schedule adherence of a vehicle reduces boarding probability for multiple reasons. One reason is the direct disutility of excess wait times. If I'm unsure when my boarding vehicle is going to come, and if it might come late, there's a lot of people who really don't like waiting in uncertain situations, and especially if they, expected to wait 5 minutes, and now it's been 8, 10, 15 minutes, they get really nervous, and they are going to directly do something else and try to avoid that possibility. The methods that I found for the highway travel can address that factor, but there's 2 other factors which it can't address. The first is missed connections. If my arriving vehicle is late to a transfer point and a vehicle that I wanted to board has already departed, then I might not actually be able to board that vehicle at all. And it has nothing to do with whether I liked that vehicle or not. That attributes of that possibility might be really good. The utility of taking that alternative might be really high, but because of the transit operations, I might have got there late, and so I can't board the vehicle. So it's not really even a behavioral issue, it's an operations issue. And the Logit model, just as I presented earlier, can't address that operational issue because it's assuming that people are choosing between vehicle, all vehicles at the same time rather than looking at the dynamic factor. And then finally, there's the lateness that a vehicle will arrive in the sequence of vehicles that arrives at my stop. So if I arrive at the stop, then let's say there's two vehicles available to me, and one I really like, and the other one I don't like so much, but it's only slightly worse. So I'm considering it, but then if the desirable vehicle gets there first, then obviously I'm going to board that vehicle. But if the undesirable vehicle arrives at my stop first, I might actually board that vehicle because it's there first, and I don't want to wait for the next vehicle, especially if that desirable vehicle, express vehicle, has a high probability of being late, then I'm going to be especially likely to board the vehicle, which is here now because I have it available to me. So just using the variability of travel times or a reliability term in the utility function, I don't think is going to solve this problem. It requires dynamic choice probabilities where the traveler adjusts their probability of choosing alternatives based on the sequence of vehicles that have arrived and what time it is right now. I developed a model which is similar, like I said, to what the problem that Mark Hickman looked at in 1993, which with some simplifications and some extensions. One of the simplifications is that I'm requiring the arrival distributions to be exponential. One of the extensions is that I'm also including variability in people's preferences in addition to variability in the arrivals of the vehicles. So what I have here is I'm imagining that this black distribution is the distribution of arrival times of my alighting vehicle, K. So this vehicle is very reliable. I know very precisely when it's going to arrive. Maybe it's a train, for example. And the other red, blue, and green arrival time distributions represent buses, perhaps, that I want to board when I arrive at the train station. So now this red line seems to be pretty frequent, but perhaps since it's so frequent, it doesn't dwell at all at the train station. When it arrives, this is a particular realization of the departure of that red vehicle, it just leaves. And so when it just leaves, then I have a high likelihood that I'm not going to be able to board that vehicle when I arrive at the train station. Perhaps the blue and the red vehicles, though, when they arrive at the train station, they dwell there because there's a time transfer to allow passengers to transfer from the rail vehicle to the blue line and the green line because they're more infrequent. So what I have here is supposed to represent a particular realization of these random arrival times. So the red vehicle arrived here, the blue vehicle and the green vehicle are dwelling, and I arrive at the train station at this time, and I don't know when these vehicles are going to come, but I know that this is what their arrival time distributions are going to be like. The question is, what is the chance that I get on the blue vehicle or the green vehicle instead of waiting for the red vehicle, which is going to come in a few minutes, hopefully? So in the model that I developed, the probability of boarding a dwelling vehicle is based on, so it's a logit. Okay, I don't know how to do this. It gets really complex, but I'll try anyway. The probability of boarding vehicle A after alighting from vehicle K depends on the sets. So A is the set of, A underbar is the set of vehicles that have already departed. A star is the set of vehicles that are dwelling. And A overbar is the set of vehicles which haven't arrived. The probability of boarding vehicle A when I arrive, given those sets of vehicles, is a logit where I have the utility of the dwelling vehicle in the numerator and the sum of the exponentiated utilities of the dwelling vehicles and the exponentiated expected utility of waiting. So I'm comparing the attractiveness of the vehicles which are here and waiting and dwelling, and then I'm comparing that utility with my expected utility for reaching the destination if I sit at the transit stop and don't board the dwelling vehicles. So the question is, what's that expected utility of waiting? This is a really complex question, but I developed a recursive formula based on the possible sequences of arrivals, and it's dependent on the conditional distribution of my arriving vehicle given the set of vehicles which have yet to arrive. So basically, I look at the distribution of the probability that I've arrived at the stop at a particular time given which vehicles I have yet to arrive. And it depends on the conditional probability that the next arrival is a particular vehicle. So if I want to know, this is the probability that the next vehicle to arrive is going to be AI. And then it also depends on the expected utility of waiting for AI. So let's say I decided that I wanted to take that particular vehicle which has yet to arrive, then I want to know the expected utility of waiting there. And I've created, like that instantaneous utility, little v from the recursive logit model, I've created another function, w, which now depends on the time that I've arrived at the stop. And so that expected utility of waiting can be found by integrating the utility of waiting from a particular time over the conditional distribution of the arrival times of the vehicle that I arrived on. And then so the probability that I board one of these later vehicles, given that I've waited, is equal to the probability that it's the next vehicle times the probability that I board the vehicle if it's the next vehicle, plus the probability that I wait times the probability that I board the vehicle given that I waited. So this is a big recursive formula to calculate the expected utility of waiting. And then finally, the marginal probability of boarding a vehicle looks at all these possible combinations of arrival sequences. And so, I look at all the vehicles in the set of vehicles I can board, and then I look at the combinations of, I look at a combination of vehicles that arrived or departed before I get there, and a combination of vehicles which I'm waiting to arrive after I've arrived. I calculate that probability, and then I multiply it by the probability of boarding it, given that it's dwelling, plus the probability that I don't board it, or that I don't board any of the dwelling vehicles, times the probability that I board it, given that I wait. And if the delays for the arrival times are independent, exponential, random variables, then there's a closed form solution for this equation, but it's like it would take 5 slides just to show you what it is, so I think I'll save that. Thank you very much, and I would like to thank also these sponsors, collaborators, and people who I've talked with about this problem. Thank you very much. Do you have any questions now? Bud?
Well, when you talk about the evaluation of upstream and downstream segments, how are you defining a segment?
So
a path segment.
A path segment, there's any sequence of links that would, for the downstream path segments, any sequence of links that would get me to my destination. And the path segment, upstream path segment, is any sequence of links ending at the link that I'm at that would have led me there from the origin.
So these are just links as we conventionally define them, and they're not weighted by some size term or anything?
No. Yeah, yes, there are how you would conventionally defined links in the transportation network. There's an issue here that, how the network is defined is going to be really important for transit, for what variables you can measure. Because if I don't have my transfers connected everywhere, if I have little walking links in between them, and those in the schedule-based transit paradigm, those links aren't actually indexed by the time, then there's no way to measure the wait time for that transfer in the link-based paradigm. So how the links are defined is tricky, but it doesn't involve any scaling at the base without what I've shown you here. Ben?
Have you implemented it? Can you give us an idea for the real network that your ultimate goal is to implement this on, and the run times and some of the issues you've dealt with to do that efficiently?
Okay, so this has not yet been implemented. The plan is to use the GTFS data for the San Francisco Bay Area with some additions that the agencies are making to work with fast trips. It's going to, I don't know, there's still a discussion, and this, basically what I present to you here, represents my opinion at this point, and we still haven't actually, I don't have the rubber stamp on this as, this is what we're going to do. So I think there's some issues with the reliability approach here, whether that is computationally feasible in a reasonable time, I'm unsure about. But everything else, I'm pretty confident that it will work efficiently. The recursive logit model, there's some really great, the stabilized biconjugate gradient solutions to that equation, which converge really quickly. So you can have a very large network and still find a solution to that efficiently.
Okay, so you mentioned briefly about the algorithm not having a sense of the stickiness of a path, right? You don't have, it's not a path choice where this path has 3 transfers and that path has 2 transfers. Have you thought about how to deal with that within the algorithm, that maybe there's a way to deal with that so that you're not getting people switching too much at any given transfer point?
Because you're thinking that the kind of marginal disutility of transfers would increase as you've had more transfers or something like that. I have thought a little bit about that, especially with regard to fares, because fares are usually not link or transfer additive. Like if you imagine I have a bus trip and then I get on the train and then I take another bus, I don't pay a fare when I transfer from the train to the bus because I already paid it when I got on the first bus. There's a couple ways to deal with this. One is to go back to look at it like a Markov decision process. And the problem there then is that the Markov property isn't satisfied because the probability of choosing the vehicle depends not only on my current state but stuff that happened before. You can actually bring the Markov property back by augmenting the state so that when I get on the vehicle, the first bus, I'm now in a new alternate reality where the state has changed because I paid that fare. And then it's basically like you almost have a gateway into another copy of the network, which just represents the possibilities that you can access after you've already paid the fare. And there's actually a couple more ways to deal with it. But I think we might be out of time, or they said they were going to stop me at 1. I'm happy to take more questions, but I just didn't want to go more into it.
Well, those other questions you can probably talk to you after.
Yeah, I would be happy to talk to anyone.